So now let's look at 3D XYZ with a plane. As you can see, we have a ground, or let's call this the XY plane. So let's just make it more clear. Let's actually put all the walls in this building or in this system here. So here I have we call this the YZ plane. And this one here, we have the XZ plane. So as you can see, there are 8 octants, or we have 8 rooms. So as you can see here, I wrote down the vector 1, 1, 1 and 2, 2, 2. So basically 1, 1, 1, 2, 2, 2, they are vectors in the front room to the right and on the top floor. So I'm just going to slightly rotate this so you can see what's happening. So focus on the right room. And as you can see here, imagine something coming out right out of your screen right now. So there's your vector. All right. So now it's kind of, I know it's difficult to see in 3D, but you just kind of had to imagine this. So imagine me taking these two vectors. So I can tell you right now that 1, 1, 1 and 2, 2, 2, you can express the red one here. As you can see here, the red one seems to be longer than the blue one. It's twice. So the red is equals to twice the blue. So previously, I'm going to take these two vectors, I'm going to add, subtract them, and see what happens. Let's just say u plus v. What happens? So see this black vector here, it's popping out at you. So I'm going to put this on the side. You can tell right away that these three vectors, they're all collinear to each other. It's the same idea from 2D to 3D. If I were to take these two vectors and subtract them, you're going to get a vector which is somewhere on the other side in the lower bottom right-hand corner, and you can't really see it. Over here, let's just say I doubled it and then I put a plus in front. What's going to happen? So I'm doing linear combinations in 3D. So now you have another vector that's a little bit longer than the one before. If I put a 3 in front of the v, make it longer. So it's going to have even more longer. If I subtracted it, all right, so over here, I'm just going to move this here. So you see that black dotted vector? So it seems like it's going into the other room, but if you notice here, no matter what I do, it seems like they are parallel to each other. All right, let's go back. So the idea is that these two vectors, the blue and the red that I had initially, they are dependent, collinear, parallel, and no matter what I do, when I talk about what I do, I'm talking about linear combinations and multiplying them, subtracting them, doing whatever I want, I end up getting a vector that's also parallel to the red and the blue. So that means these two vectors, the red and the blue, they do not span. Meaning spanning means you have to cover a certain surface area, and it seems like it's only going in one or the other direction. It has to be able to go in other directions where I want it to go. So here we have a vector, same thing as before, 1, 1, 1, but now instead of 2, 2, 2, we have 1, 2, 3. So I can tell you right now that these two vectors, they're not dependent on each other, they're independent. And even in the picture you can see here, as I sort of rotate this, they don't seem to be parallel to each other in 3D. One seems to go in a different direction and a different angle to each other. All right, so let's actually bring this back into, it's kind of difficult to maneuver this. All right, so let's just do it this way. All right, so here we go. So this room here in front is the quadrant 1. Well, it's not called quadrant 1, it's called octant 1, the one facing you, all positive octant. All right, so let's actually play around with this. Let's do some linear combinations with this. So let's take the u vector and add them and see what happens. Okay, so you have a vector here. As you can see, it's not parallel to the other ones. Let's do another one. I'm going to keep on doing some linear combination. Let's do u minus v. All right, so you see this little black one down here. I'm going to keep on going with this. Let's move on. Let's do double and then plus, let's just say v. Let's see what happens. So the idea is I'm going to get a bunch of vectors. Let's do negative 2u and then minus v, all sorts of combinations. Let's do double negatives. All right, let's do a v minus w, 2w. All right, let's do 3v minus 4u. Doesn't matter what it is. All right, so I'm just doing some different combinations. Now let's do one more. Let's do negative v plus 2u. We did that already. It doesn't matter. So what's happening is that we're creating vectors that are going all over the place. And you probably think, well, okay. But what's interesting about these vectors is if you're to maneuver this around, all right, so as you can see, all these black vectors, the dot and the solids, they're all going in different directions comparing to the blue and the red. But if you notice, they do line up. Oh, right there. They do line up in 3D. So what that means is they actually span a plane. You're probably wondering, what is a plane? Well, a plane, imagine as a wall. Now keep in mind these planes, there's planes all over in 3D. So what you see right here is a gray plane, the one on the floor, but now we have I can tell you that it's a slanted plane. And what I'm going to do right now is I'm going to show you what this plane looks like. So don't worry about this equation. So here we have a blue plane, a blue slanted wall in 3 space. And on this wall, you will notice that all of these vectors that we created from the red and the blue lies on the plane. So all these vectors, even though they seem like they have nothing in common, but they do have something in common, they all lie on this blue plane. So what that means is the red and the blue vector create vectors that, sure, they don't seem like they have anything in common, but they all lie on the same plane. So therefore, the red and the blue vector, they span a plane, a specific plane.
So here we have a question which addresses 3 vectors. So the question right now is, how do you know if a vector lies on the same plane as 2 other vectors? So let's just say I had 2 vectors that are given. So look at these 2 vectors. When you look at the numbers, they're not scalar multiples of each other. Like v is not double u or u is not half of v. What that means is they are not collinear, they are independent, and therefore they span a plane in 3D. Now the question is, this third vector here, how do you know if this third vector is on the same plane as u and v? Now, from the previous slide, in order to know that something is on the same plane, the vector has to be able to be combined with u and v. So, in other words, you have to do something to u and do something to b, like a linear combination, all right? And that will give you a vector that will be on the same plane. Now, the question right now is 3, 5, 9, which is the third vector, is that on the same plane? Can we actually do something to u and v to get 3, 5, 9? So let's calculate this. You have a, u is 1, 1, 1, plus b, which is 1, 2, 3, and we want to see whether we get 3, 5, 9. So let's actually let's do the distributive property. So you have b, 2b, and 3b, which equals to 3, 5, 9. And after that, we're going to focus on the x components. So then in terms of the x components, we have a plus 2b is equals to 3. And then using the red, let's look at the y components. And the y components are a plus 2b is equals to 5. A plus 2b is equals to 5. And the last one here is going to be the z components. The z is going to be here, which is a plus 3b is equals to 9. And now we have 3 different equations. And all we need to solve for 2 variables is actually 2. So I'm just going to take these 2 and bring them together. So I'm going to bring the red one underneath the blue one here. This one should be in the B. And now I'm just going to do elimination and subtract the bottom minus the top. So 2b minus b is going to be b, which equals to 2. Now to solve for a, I'm just going to sub this back into the first blue equation. So a plus 2 is equals to 3. And therefore a is equals to 1. So now we got the values for a and b's, but we only got these 2 values from these 2 equations, the x equation and the y equation. We need to check whether it actually works for the z equation. So we're going to check. Let's sub in a for 1 and b for 2. A is 1 plus 3 times 2, and that gives us 7. Unfortunately, 7 is not equal to 9. And what that means is 3, 5, 9. 9 doesn't fit. 9 does not fit. So what that means is 3, 5, 9 is impossible to get from a linear combination from these 2 vectors, because 3, 5, 9 is not a vector produced from the linear combination. That means 3, 5, 9 is not a vector on the same plane, meaning it is not coplanar to vectors u and v.